Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Pluto, once considered the ninth planet of our solar system, occupies a unique and fascinating place in the cosmos. Its story is not only one of scientific discovery, but also one of debate, controversy, and the evolving understanding of what constitutes a planet. Discovered in 1930 by the astronomer Clyde Tombaugh at the Lowell Observatory in Arizona, Pluto was initially celebrated as the long-sought Planet X, a celestial body predicted to exist beyond Neptune to explain irregularities in the orbits of the outer planets. For decades, it held a privileged position in textbooks, in the imagination of the public, and in the hearts of astronomers who marveled at its distant, icy presence. Pluto is small, measuring about 2,377 kilometers in diameter, which is roughly two-thirds the size of Earth's moon. Its diminutive stature, however, does not diminish its intrigue. Pluto's orbit is highly elliptical, taking it from approximately 30 astronomical units to 49 astronomical units from the Sun, meaning it sometimes comes closer to the Sun than Neptune and sometimes drifts far beyond. Its orbital path is tilted relative to the plane of the solar system, giving it a path that seems almost rebellious when compared to the near-circular orbits of the classical planets. This eccentric orbit adds to Pluto's mystique and has made it an object of fascination since its discovery. One of Pluto's most compelling features is its complex system of moons, chief among them Charon. Discovered in 1978, Charon is extraordinary in that it is nearly half the size of Pluto itself, making the Pluto-Charon pair a true binary system rather than a typical planet-moon arrangement. The gravitational interaction between the two creates a situation in which both bodies orbit a barycenter located outside of Pluto, a rare phenomenon in the solar system. Beyond Charon, Pluto has four smaller moons: Styx, Nix, Kerberos, and Hydra, each adding to the gravitational and dynamical complexity of the system. Observations of these moons have revealed surprising insights into Pluto's formation and the violent past of collisions and accretions in the Kuiper Belt. The surface of Pluto is a patchwork of astonishing landscapes, composed primarily of nitrogen, methane, and carbon monoxide ices. Images captured by the New Horizons spacecraft, which performed a historic flyby in July 2015, revealed a heart-shaped region named Tombaugh Regio, covered with smooth nitrogen ice plains. This area is characterized by glaciers, possible cryovolcanoes, and a surprising lack of impact craters in some regions, suggesting ongoing geological activity. Such findings were unexpected for a body so far from the Sun, challenging earlier assumptions that small, icy worlds are geologically dead. The presence of diverse terrains, from rugged mountains made of water ice to vast plains of frozen nitrogen, paints a portrait of Pluto as a dynamic world in its own right, with internal heat, seasonal changes, and possibly even a subsurface ocean beneath its icy crust. Pluto's thin atmosphere is primarily composed of nitrogen, with traces of methane and carbon monoxide. Unlike the atmospheres of larger planets, Pluto's atmosphere is extremely tenuous, with surface pressure a fraction of that found on Earth. It is sensitive to its distance from the Sun, expanding when Pluto approaches perihelion and collapsing onto the surface as frost when it moves farther away. Observations of atmospheric escape, where gas gradually leaks into space, reveal that even in the frigid outskirts of the solar system, processes like solar wind interactions and atmospheric dynamics are actively shaping Pluto's environment. The reclassification of Pluto as a dwarf planet in 2006 by the International Astronomical Union, IAU, was a watershed moment in planetary science. This decision reflected a growing understanding of the solar system's complexity. A dwarf planet, by IAU definition, is a celestial body that orbits the Sun, has sufficient mass for its self-gravity to assume a nearly round shape, but has not cleared its orbital neighborhood of other debris. This nuanced definition acknowledges that the solar system is more diverse than a simple count of planets can express. The change sparked public debate and even a sense of loss, with many still fondly referring to Pluto as the ninth planet. Yet, scientifically, it opened a new frontier, highlighting that Pluto is part of a larger family of small, icy worlds that populate the Kuiper Belt beyond Neptune. The Kuiper Belt itself is a vast, donut-shaped region of the solar system, populated with tens of thousands, possibly millions, of icy bodies ranging from tiny rocks to dwarf planets like Pluto. This region is a remnant of the primordial disk of material from which the planets formed. Objects in the Kuiper Belt, often called Kuiper Belt objects or KBOS, provide crucial clues to the early history of the solar system. They are composed of primordial ices and rock, largely unaltered by internal heating or collisions, making them time capsules from the solar system's formation 4.6 billion years ago. In many ways, studying Pluto allows scientists to understand not only a unique world, but also the broader context of solar system evolution and the diversity of planetary bodies. Other dwarf planets in our solar system, including Eris, Haumea, Makemake, and Ceres, share similarities and differences with Pluto. Eris, slightly smaller than the Pluto but more massive, resides far beyond the orbit of Neptune, within the scattered disk, a region overlapping the Kuiper Belt but with more eccentric orbits. Haumea, known for its elongated, football-like shape and rapid rotation, possesses a ring system, while Makemake, slightly smaller than Pluto, has a reddish surface indicative of methane ice. Ceres, the only dwarf planet located within the asteroid belt between Mars and Jupiter, is markedly different, a rocky and icy world with evidence of water ice and possible past cryovolcanism. The study of these dwarf planets broadens the concept of what a planetary body can be and emphasizes the diversity of conditions and evolutionary paths in our solar system. Pluto's reclassification also reshaped how astronomers search for and study distant worlds. The recognition that the Kuiper Belt hosts many large, icy bodies similar to Pluto led to intensified searches for additional dwarf planets and small planets beyond Neptune. These efforts are revealing a complex dynamical system in which gravitational interactions with Neptune and each other sculpt the orbits and physical characteristics of these distant objects. The discoveries of Sedna and other extreme trans-Neptunian objects hint at the possibility of yet undiscovered massive planets lurking in the distant reaches of the solar system, rekindling the spirit of exploration that led to Pluto's initial discovery. Beyond scientific significance, Pluto holds a special place in human culture. It has inspired generations of astronomers, writers, artists, and dreamers who see in its distant, icy world a symbol of exploration and curiosity. Pluto's story embodies the human desire to understand the unknown, to push the boundaries of knowledge, and to reconcile our intuitive sense of order with the complexity revealed by observation. It stands as a testament to the evolving nature of science, where definitions and classifications are refined in light of new evidence, and where a small, distant world can provoke debates as intense as those surrounding the largest planets. The ongoing study of Pluto and the dwarf planets continues to yield surprises. New Horizons data remains under analysis, revealing subtle features such as seasonal changes, interactions with the solar wind, and the composition of its minor moons. Future missions may one day return to Pluto or explore other Kuiper Belt objects, offering a more detailed understanding of the chemical and physical processes operating in the outer solar system. As observational technology improves, the line between planets and dwarf planets may blur even further, reminding us that nature often defies simplistic categories. Pluto's story also illuminates the dynamic interplay between discovery, technology, and theory. Early astronomers inferred its presence through mathematical predictions and meticulous observations, highlighting the power of deduction in science. Space missions like New Horizons transformed abstract points of light into richly detailed worlds with mountains, valleys, plains, and atmospheres. Each advancement in technology, from telescopic improvements to spacecraft instrumentation, has brought us closer to understanding the distant reaches of our solar system. The narrative of Pluto exemplifies how scientific knowledge evolves incrementally, shaped by observation, interpretation, and the willingness to challenge assumptions. In many ways, Pluto serves as a gateway to understanding the broader solar system. Its complex geology, dynamic atmosphere, and diverse satellite system offer a microcosm of planetary processes. Its location in the Kuiper Belt, provides context for the formation and migration of planets, while its classification as a dwarf planet encourages a re-examination of what it means to be a world. Each discovery about Pluto reverberates through planetary science, informing models of planetary formation, atmospheric chemistry, and orbital dynamics. Through Pluto, the outer reaches of the solar system become more tangible, bridging the gap between the familiar planets and the mysterious expanse of icy bodies beyond. Dwarf planets like Pluto also expand the concept of habitability and the potential for exotic environments. While Pluto is far too cold and distant to support life as we know it on Earth, the presence of internal heat, possible subsurface oceans, and complex organic chemistry raises intriguing possibilities. Similar processes may exist on other icy bodies in the solar system, including moons of the giant planets such as Europa, Enceladus, and Titan, suggesting that the study of dwarf planets contributes to the broader search for life in the cosmos. Understanding these distant worlds helps us explore the diversity of planetary conditions and the ways in which life, if it exists elsewhere, might adapt to extreme environments. Pluto's tale also reflects humanity's emotional connection to space. The debates surrounding its status, the affection felt for this small, distant world, and the excitement generated by the New Horizons mission all underscore the deep cultural significance of astronomical discovery. Unlike any other, Pluto embodies a narrative of resilience and wonder. A small body, once demoted, yet commanding immense fascination and inspiring a sense of cosmic perspective. It reminds us that science is not only a pursuit of knowledge, but also a story about curiosity, imagination, and the human spirit. As research into the Kuiper Belt and dwarf planets continues, new frontiers emerge. Astronomers are now cataloging hundreds of Kuiper Belt objects, studying their compositions, rotations, and interactions. They are exploring the implications of these findings for planetary formation, migration patterns of the giant planets, and the long-term evolution of the solar system. Each dwarf planet discovered adds to a growing family of celestial objects, challenging our traditional notions of planets and expanding the tapestry of worlds we recognize as part of our cosmic neighborhood. Pluto, once the pioneer of this journey, continues to guide our understanding of the outer solar system and inspire exploration into the unknown. The legacy of Pluto and the dwarf planets extends beyond the realm of science. These distant worlds challenge our perception of scale, distance, and the nature of planetary identity. They teach us humility in the face of the vastness of space, patience in the pursuit of discovery, and wonder at the richness of the universe. The story of Pluto is ultimately a story of exploration, adaptation, and curiosity, a testament to the enduring human desire to look beyond the familiar, to question assumptions, and to seek understanding among the stars. Pluto's journey from discovery to reclassification, from an unknown point of light to a richly detailed world, mirrors the evolution of human knowledge. It illustrates the importance of questioning, observing, and revising ideas based on evidence. The dwarf planets collectively expand the definition of what a planetary body can be, revealing a diversity of forms, compositions, and behaviors. They are reminders that the solar system is not a static, simple arrangement of planets, but a dynamic, evolving collection of worlds, each with its own story, its own characteristics, and its own mysteries waiting to be explored. Pluto stands as the emblem of this outer frontier, a symbol of discovery that continues to captivate scientists and the public alike. As our exploration of the outer solar system progresses, we may discover even more distant, massive objects that challenge the current boundaries of planetary science. The search for Planet 9, hypothetical massive objects influencing the orbits of distant Kuiper Belt objects, hints at how much remains hidden in the dark reaches beyond Neptune. Each new discovery promises to reshape our understanding of the solar system's architecture and history, reinforcing the idea that science is a continuous journey rather than a fixed set of facts. In this journey, Pluto remains a vital guide, a small yet powerful symbol of human curiosity and the thrill of exploration. Pluto's surface is a remarkable mosaic of terrains that tell a story of both ancient history and recent activity. The most iconic feature, Tombaugh Regio, the heart-shaped plain, stands out not just for its shape, but for what it reveals about Pluto's internal dynamics. Composed largely of nitrogen ice, this vast plain is geologically young, indicating that Pluto's surface is still being reshaped by processes that involve the slow movement of ices. Within this region lies Sputnik Planitia, a massive, smooth basin covered with convective cells that resemble giant polygons. These patterns are formed as nitrogen ice slowly flows and overturns, a process analogous to glaciers on Earth, but occurring in extreme cold at temperatures near -230 degrees Celsius. This active ice tectonics demonstrates that even small worlds in the outer solar system can have energy sources sufficient to drive resurfacing, challenging previous assumptions that only large planets with thick atmospheres or moons with tidal heating could show such activity. Surrounding Tomball Regio, Pluto presents a variety of other fascinating terrains. To the west, towering mountains rise from the icy plains, composed mainly of water ice which behaves like rock at Pluto's frigid temperatures. These mountains reach heights of up to 3,500 meters, rivaling the Rockies on Earth. Their formation is likely the result of ancient tectonic forces or cryovolcanism, a phenomenon where icy lava emerges from below the surface. The presence of mountains alongside smooth plains and valleys suggests a dynamic and complex geological history that has persisted for billions of years. Elsewhere, craters indicate regions of older, less active terrain, providing a record of impacts and collisions that have shaped Pluto over its long existence. Pluto's small size and distance from the Sun would seem to preclude any atmosphere, yet it maintains a tenuous envelope of gases, primarily nitrogen, with traces of methane and carbon monoxide. This atmosphere is in constant flux, responding to Pluto's elliptical orbit. When closer to the Sun, the ice sublimates, thickening the atmosphere. When farther away, gases freeze and settle back onto the surface. Such seasonal behavior creates phenomena akin to winds, frost, and haze layers that drift over its surface. The New Horizons mission revealed blue atmospheric haze extending hundreds of kilometers above the surface, composed of complex hydrocarbons formed by interactions with sunlight. These findings show that Pluto is far more than a frozen rock. It is a world with active atmospheric chemistry and processes reminiscent of larger planets. The binary nature of Pluto and Charon adds yet another layer of complexity. Charon, nearly half the size of Pluto, exerts significant gravitational influence, resulting in a mutual tidal lock, where both bodies show the same face to each other. This lock dance creates unique gravitational effects that shape surface features, such as potential fractures and canyons on Charon. Observations suggest Charon itself may have a subsurface ocean, a testament to the presence of heat sources despite its frigid environment. The smaller moons, Styx, Nix, Kerberos, and Hydra, while diminutive, offer insight into the history of collisions and accretion in the Pluto system. Their irregular shapes and chaotic rotations indicate that they may be remnants of a massive impact event early in Pluto's history, which also contributed to the formation of Charon. Moving outward from Pluto, the Kuiper Belt emerges as a vast and mysterious region populated with icy worlds. Pluto is the largest known member of this region, but it is far from alone. Eris, discovered in 2005, is a distant, massive dwarf planet with a highly elliptical orbit that extends nearly 3 times as far from the Sun as Pluto at its aphelion. Slightly smaller in size but more massive than Pluto, Eris has a surface coated with frozen methane, giving it a bright, reflective appearance. Its discovery was a pivotal moment, prompting the re-evaluation of Pluto's status and spurring the formal definition of a dwarf planet. Eris is accompanied by a moon, Dysnomia, which helps astronomers determine its mass and composition. The study of Eris provides a glimpse into the diversity of objects that inhabit the outer reaches of the solar system and emphasizes the richness of the Kuiper Belt. Haumea, another intriguing dwarf planet, is notable for its unusual shape. Rapidly spinning on its axis, it has an elongated, football-like appearance, a result of centrifugal forces that stretch its icy body. Haumea's surface is covered with crystalline water ice, which suggests relatively recent resurfacing, since crystalline ice is unstable over long periods in the cold vacuum of space without some internal or external process to reform it. Haumea also possesses a ring system, an unexpected feature for a body of its size, and two moons, Hayaka and Namaka, each providing clues about its formation and collisional history. Its rapid rotation and the presence of moons point to a violent past, possibly involving a catastrophic impact that shaped both its structure and its satellites. Makemake, slightly smaller than Pluto, presents yet another variation on the dwarf planet theme. Its surface is coated in methane ice with hints of ethanohone and other hydrocarbons, giving it a reddish hue. Unlike Pluto and Haumea, Makemake shows no obvious signs of a substantial atmosphere, though observations suggest a very thin layer of gas may exist temporarily during its orbit's perihelion. Makemake's discovery further underscored the idea that the outer solar system is populated with many large, icy bodies, each with its own characteristics, orbits, and histories, forming a family of worlds that challenge traditional definitions of planets. Closer to the Sun within the asteroid belt resides Ceres, the only dwarf planet in the inner solar system. Discovered in 1801 by Giuseppe Piazzi, Ceres is a rocky and icy body, significantly different from its distant icy counterparts. With a diameter of about 940 kilometers, it is smaller than Pluto, but holds particular scientific interest due to evidence of water ice and past cryovolcanism. Bright spots observed on its surface, most notably in the Occupies crater, are salt deposits left behind by briny water that reached the surface and sublimated, leaving behind reflective material. This suggests that Ceres has an active geological history and a potential subsurface ocean, raising questions about the possibility of past or even present habitability. Its study provides a bridge between the icy dwarf planets of the Kuiper Belt and the rocky worlds of the inner solar system. The discovery and study of these dwarf planets have transformed our understanding of the solar system. Rather than a simple arrangement of 9 planets orbiting the Sun, astronomers now see a diverse collection of bodies ranging in size, composition, and orbit, each telling a story of formation, migration, and evolution. The Kuiper Belt, scattered disk, and the inner asteroid belt reveal a solar system that is both dynamic and complex, shaped by billions of years of gravitational interactions, collisions, and subtle shifts. Dwarf planets in particular highlight the variety of pathways through which small worlds can evolve, retain atmospheres, and exhibit geological activity despite their modest sizes. The New Horizons mission to Pluto marked a turning point in our direct understanding of the outer solar system. Prior to this mission, Pluto was merely a point of light in telescopes, its features inferred through careful observation. The flyby provided high-resolution images, detailed spectral data, and insights into its moons and environment, transforming Pluto into a real, tangible world. Beyond Pluto, New Horizons continued into the Kuiper Belt, performing a close flyby of Arakoth, previously known as 2014 MU69, in 2019, a contact binary object that offered clues to the early stages of planetesimal formation. Observing Arakoth allowed scientists to see a pristine relic from the solar system's infancy, helping to contextualize the formation of Pluto, Eris, and other distant bodies. The mission's findings are still being analyzed, promising decades of scientific discovery and reshaping our understanding of small, icy worlds. Pluto and the dwarf planets also offer critical insight into planetary atmospheres and surface chemistry. Despite their distance from the Sun, these bodies exhibit complex interactions between surface ice and tenuous atmospheres. Sublimation and deposition cycles, chemical reactions driven by ultraviolet light, and escape of gases into space are common processes that shape these environments. Methane, nitrogen, and carbon monoxide ices on Pluto, Makemake, and Eris interact with solar radiation to create complex hydrocarbons, potentially forming reddish tholins that coat their surfaces. These processes mirror, in miniature, the chemical pathways that may occur on other icy worlds throughout the universe, linking the study of dwarf planets to the broader field of astrochemistry and the search for prebiotic molecules. The study of dwarf planets also informs theories about planetary formation and migration. The Kuiper Belt and scattered disk objects suggest that the giant planets, particularly Neptune, migrated outward early in the solar system's history, scattering smaller bodies into distant orbits. This migration model explains the current distribution of objects like Pluto, Eris, and Sedna, whose eccentric and inclined orbits would be improbable without significant gravitational perturbations. By studying the size, composition, and orbital dynamics of these dwarf planets, astronomers can reconstruct the early solar system's architecture, gaining insight into how the planets arrived at their current positions and how similar processes might occur in other planetary systems. Culturally, Pluto holds a special place. Its demotion from planet to dwarf planet sparked passionate debate among scientists, educators, and the public, highlighting the intersection of science and human perception. People have long felt a sense of personal connection to Pluto, seeing it as the little planet that could, and as a symbol of curiosity and discovery. It has inspired art, literature, and even music, reinforcing the idea that astronomical objects are not only scientific entities, but also touchstones for imagination and wonder. Pluto's story exemplifies how scientific classification interacts with culture, shaping the way humans engage with and relate to the cosmos. As exploration continues, astronomers hope to learn more about the diversity of dwarf planets. Future missions may target Eris, Makemake, or Haumea, revealing details about their geology, atmospheres, and potential moons. Advancements in telescopic observation, including space-based infrared and optical instruments, will allow more precise measurements of their compositions, surface temperatures, and orbital dynamics. The ongoing discovery of trans-Neptunian objects suggests that many more dwarf planets await classification, each offering unique insights into the processes that shape the solar system. As we expand our knowledge, the line between planets, dwarf planets, and other small bodies may continue to evolve, reflecting the growing complexity of our understanding. Pluto, with its icy plains, mountains, and atmosphere, serves as a gateway to the outer solar system. Its study has illuminated the processes that govern small, distant worlds, from geological activity to atmospheric chemistry, and has expanded the concept of what constitutes a planet. The broader family of dwarf planets demonstrates the diversity of celestial bodies that exist beyond the classical planets, each shaped by collisions, gravitational interactions, and the subtle forces of the outer solar system. Together, they challenge traditional definitions, expand our knowledge, and inspire ongoing exploration. Pluto and its fellow dwarf planets remind us that the solar system is not a simple collection of 9 planets, but a dynamic, evolving system full of surprises, variety, and complexity. These distant worlds, though small in size, are enormous in the lessons they offer, revealing the richness of processes that operate across time and space. From icy plains and mountains to tenuous atmospheres and binary systems, they challenge assumptions, spark curiosity, and offer a window into the early solar system. Each discovery reinforces the idea that exploration is never finished, and that even the smallest worlds can illuminate the grandest questions about our place in the cosmos. Pluto's journey from a point of light in the sky to a richly characterized world, surrounded by moons and accompanied by a growing family of dwarf planets, exemplifies the power of scientific inquiry. Its story illustrates that discovery often leads to more questions than answers, and that redefining boundaries, whether of planets, dwarf planets, or the solar system itself, is a natural part of understanding. In studying Pluto and its peers, humanity gains not only knowledge of distant worlds, but also perspective on the processes that shaped our own planet, the Sun, and the diverse array of bodies that orbit it. The outer solar system, once shrouded in mystery, is now a realm of ongoing exploration, where every new observation offers insight into the origins and evolution of planetary systems. Pluto and the dwarf planets are not merely curiosities at the edge of our solar system, they are key to understanding planetary science as a whole. They offer models for the formation of planets, moons, and other small bodies, demonstrating the interplay of gravity, collisions, and chemical processes over billions of years. They reveal that geological activity is possible even on small, distant worlds, and that atmospheres can persist under extreme conditions. They challenge simple definitions, inviting us to refine our classifications as our knowledge grows. Above all, they embody the human drive to explore, understand, and imagine, reminding us that the universe is more varied and complex than we can ever fully grasp. Pluto and its fellow dwarf planets, while small in size, continue to inspire awe and curiosity, serving as gateways to the outer reaches of our solar system. As exploration progresses, scientists anticipate uncovering even more distant worlds, each potentially harboring unique features, moons, and geological histories. The discovery of new trans-Neptunian objects suggests that the outer solar system is far more crowded and complex than once imagined, and that Pluto is but the first of many intriguing worlds waiting to be studied. These distant bodies challenge our understanding of planetary formation, migration, and evolution, offering insights into how the solar system attained its current structure. The continued study of Pluto and other dwarf planets also informs our understanding of exoplanets and planetary systems beyond our own. Observing the diversity of small, icy worlds in the Kuiper Belt allows scientists to draw parallels with planetary systems orbiting other stars, where icy bodies, moons, and distant planets may follow similar dynamical processes. By studying Pluto's atmosphere, surface, and moons, astronomers gain a template for understanding distant, cold worlds that cannot yet be observed directly. This comparison not only broadens the context of planetary science, but also deepens our understanding of how common or rare certain features and processes may be across the galaxy. Pluto's story is also a powerful example of the evolving nature of science. From its discovery as the so-called ninth planet to its reclassification as a dwarf planet, Pluto illustrates how scientific definitions are not fixed but adapt in response to new evidence and understanding. Its redefinition prompted debates, revisions of textbooks, and discussions in classrooms worldwide, highlighting the way science intersects with culture, perception, and education. Yet rather than diminishing Pluto's significance, its status as a dwarf planet has elevated the study of small worlds, drawing attention to the complexity, diversity, and dynamism of the solar system beyond the traditional planets. Looking to the future, missions to Pluto, the Kuiper Belt, and other distant regions promise to revolutionize our knowledge even further. Technological advances in telescopes, spacecraft, and instrumentation will allow more detailed observations of dwarf planets and their moons, shedding light on their composition, atmospheres, and internal structures. Potential future flybys, orbiters, or even landers could reveal whether subsurface oceans exist, how geologic and atmospheric processes operate at extreme distances from the sun, and what chemical and organic processes are active on these icy worlds. Each new mission brings the promise of discovery, reminding us that Pluto's journey from an unknown speck to a richly characterized world is just the beginning of humanity's exploration of the outer solar system. In the grand tapestry of our cosmic neighborhood, Pluto and the dwarf planets occupy a vital and fascinating niche. They serve as reminders that even small and distant worlds can possess complexity, dynamism, and significance far beyond their size. Their study enriches our understanding of the solar system, informs our search for other planetary systems, and fuels our curiosity about the universe. From icy plains and mountains to tenuous atmospheres and binary systems, these worlds offer lessons in planetary formation, evolution, and diversity. They inspire the human spirit of exploration, encouraging us to look beyond familiar horizons and embrace the mysteries of the distant cosmos. Ultimately, Pluto stands as both a scientific marvel and a cultural icon. Its journey from discovery, through controversy, to renewed appreciation exemplifies the ever-evolving nature of knowledge and the boundless possibilities that lie beyond. As our gaze extends further into the outer solar system and beyond, Pluto remains a symbol of the unknown, a beacon of curiosity, and a testament to the remarkable diversity of worlds that inhabit our cosmic neighborhood. The study of Pluto and the dwarf planets not only advances our understanding of distant icy bodies, but also enriches humanity's connection to the universe, reminding us that the quest for knowledge is as infinite as the cosmos itself. With continued exploration and discovery, Pluto and its fellow dwarf planets will remain at the forefront of scientific inquiry, guiding humanity in its pursuit of understanding the origins, evolution, and nature of the solar system. They remind us that even the smallest worlds can hold the greatest mysteries, and that every object, no matter how distant or dim, has a story to tell. Through these stories, we come to appreciate not just the complexity of the cosmos, but also our own place within it, as explorers, observers, and learners in an ever-expanding universe.